Okay, so in this video, we're going to have a look at question 8b from the 2003 HSC Extension 2 exam. And this is the very final part of the final question, so you can expect it's going to be quite a tough one. So let's have a look. Suppose that pi could be written in the form p on q, where p and q are positive integers. Define the family of integrals in for n equals 0, 1, 2, and so on by that expression there, and you are given these two results, I0 equals 2, I1 equals 4q squared. We don't need to prove those. Okay, part I. Use integration by parts twice to show that for n greater than or equal to 2, we have this fairly messy result. Okay, so let's have a look. Part I, when my pen works. When my pen works, does it work? Yeah, it works. Okay. Part I. Now, our integral in is equal to q 2 to the n divided by n factorial, the integral of pi on 2, or from negative pi on 2 to pi on 2, of pi squared on 4 minus x squared to the power n multiplied by cos x dx. Okay, I need to use integration by parts. In fact, it says to use it twice, but for the first time, what is going to be my u and what is going to be my v dash? Well, if I look what I have, I can see that the power of n here, this power, n is being reduced. Here I have n minus 1, and here n minus 2, so that probably means I'm going to be differentiating this one, since that will reduce the power. Okay, so let's go ahead and do that. So, letting u be pi squared on 4 minus x squared to the n, that means u dash is going to be, okay, bring down the power, pi squared on 4 minus x squared, subtract 1 from the power, n minus 1, and multiply by the inside derivative, so chain rule, and that gives me negative 2x. Okay, and therefore that means v dash is going to be cos x, which means v is sin x. Alright, so in is equal to, now I'm leaving this q to the power 2n factorial and over n factorial just out the front, and I have what? I have u times v, so that's pi squared on 4 minus x squared to the n multiplied by sin x, and that's evaluated between my two limits, so pi on 2 and negative pi on 2, minus the integral of u dash times v. So what is u dash? U dash is negative 2xn multiplied by this. So here I have a minus, and here I have a minus, so that makes it a plus. 2n is a constant, so I'll take that out the front. My integral is of, from minus pi on 2 to pi on 2, of x, pi squared on 4 minus x squared n to the negative 1 multiplied by sin x dx. Great. Okay, let's move this out of the way for the moment. Okay, so substituting this in, well, here I have a polynomial. This is in fact a polynomial without the sin x. This is a polynomial, and the roots of this polynomial are in fact pi on 2 and negative pi on 2. So that means if I substitute both of these in, I'm going to get 0. So that means this whole term here is going to go to 0. So I can pretty much ignore this now. And what do I have? I have q to the power 2n times 2n divided by n factorial. So times 2 is fine. Now n divided by n factorial will give me n minus 1 factorial in the denominator. And then I have my integral of x pi squared on 4 minus x squared to the power n minus 1 sin x dx. And that's equal to in. And there I have used integration by parts for the first time. Now the question was nice enough to tell me I need to use it twice. So once again, I'm going to choose my u and v, and my v dash. So my u is going to be this algebraic expression, x times pi squared on 4 minus x squared to the n minus 1. X times pi squared on 4 minus x squared to the n minus 1. Because I really can't integrate this, even if I wanted to choose this as my v dash, I really can't integrate. I don't really know what the derivative of it is. And so therefore u dash is going to be, okay, so we have a product. So differentiate the first and leave the second would be pi squared on 4 minus x squared to the power n minus 1. And now leave the first and differentiate the second. Gives me x multiplied by pi squared on 4. Now I need to bring down the power, which I forgot to write, but it's not a problem. I'll just write it afterwards. N minus 1, and I need to subtract 1 from the power. And I also need the inside derivative, so that's negative 2x. Let's tidy that up a little bit. That's equal to pi squared on 4 minus x squared to the power n minus 1. Now I have a negative 2, n minus 1. I have x times x is x squared, and pi squared on 4 minus x squared to the n minus 2. So that was a bit of work in itself. That's just to work out what u dash is. And my v dash, well, that's sine x. And so my v is going to be minus cos x. Remember, when you integrate sine, it's minus cos. Okay, so now plugging these values into my integration by parts formula. So in equals, again, don't forget this bit out the front, 2q to the 2n divided by n minus 1 factorial multiplied by u times v. So that's going to be, let's have a look. Where's my u? X, these should be square brackets. X times pi squared on 4 minus x squared to the n minus 1, that's u, multiplied by v. So there's the minus for the v, cos x. And these are my limits. And you can see that once again this will go to 0 because these here are roots of this polynomial. Minus the integral of u dash v. Now, the v has a negative, so I can combine these two negatives to make it a positive. And this is my u dash, this large expression here. Now, am I going to even fit that on this line? I don't think so, so let me write it down here. Okay, putting in my limits, and I have the following. Pi squared on 4 minus x squared to the n minus 1 minus 2n minus 1 x squared pi squared on 4 minus x squared to the n minus 2 multiplied by the v. Now remember, I already put the negative of the v combining with that negative that's out the front there, so I'm just left with cos x dx. And all of that is being multiplied by 2q to the 2n over n minus 1 factorial. Alright, now, we said that this was going to go to 0 because these are the roots of that polynomial. So this term goes to 0, and I have 2q to the 2n over n minus 1 factorial multiplied by this expression. But have a look at what the question wants. We can see that we have two integrals. One of them has this polynomial to the power of n minus 1. The other has to the power of n minus 2. Here I can see an n minus 1, and here I can see an n minus 2. So I'm going to distribute the cos through this bracket here, through this bracket, and then split up into two integrals because, of course, integration is a linear operation. So, integrating this expression times cos x, pi squared on 4, minus x squared to the n minus 1 times cos x dx minus, now I'm multiplying this through the whole thing, so I have 2q 2n. We're going to struggle to fit this on this line as well, multiplied by another 2, so 2n minus 1, the integral of, alright, let's try and fit it in, x squared pi squared on 4 minus x squared to the n minus 2, no success, cos x dx. Okay, so that is very squished there, but hopefully you can follow along. I've just multiplied the cos x by this expression, and that's what I have in this integral. Okay, so I'm almost there actually. Let's bring this back. So I just need to manipulate to see this, and I've pretty much got that part done. So the first part of the expression is fine. We're at where we want to be. Integral from negative pi on 2 to pi on 2, pi squared on 4 minus x squared to the n minus 1 cos x dx. And now here, well, 2 times 2 is 4. Q to the 2n stays as it is. Now n minus 1 divided by n minus 1 factorial is n minus 2 factorial. And then I just have my integral. And that's the end of that part, because I've proven or shown exactly what they wanted. N minus 2 cos x dx. Again, it's a bit squished. But anyway, that is the first part of the question. Okay, part 2 says, by writing x squared as this expression, where appropriate, deduce that in is equal to this nice looking expression here. Okay, so we're going to be using the previous part's result, clearly because we can see this in minus 1 and in minus 2, which correspond to the n minus 1 power and n minus 2 power. But it's not as simple as that. Now it is worth 1 mark, but there's going to be a bit of work here. But first, let's write down what we actually have to prove. So we're required to prove the following. In equals 4n minus 2 q squared, in minus 1 minus p squared q squared, in minus 2. Okay, and for n greater than or equal to 2. Now I have this, but what is this really in terms of its integrals? It's nice to see it in terms of integrals instead of in terms of these i's, because that'll help us when we want to manipulate this in order to get to this. So let's just move it over here so I can fit it in. That'll be 4n minus 2 q squared. Now what's in minus 1? In minus 1 is just substituting n minus 1 wherever I see an n in this expression. So that's going to be multiplied by q to the power 2 times brackets n minus 1 divided by n minus 1 factorial, and then I have the integral of pi squared on 4 minus x squared to the n minus 1 cos x dx minus p squared q squared in minus 2. Well, in minus 2 is just substituting n minus 2 into this. So that's going to be q to n minus 2 on n minus 2 factorial, the integral of pi squared on 4 minus x squared to the n minus 2 cos x dx. Okay, so you can see that that's quite long, but not to worry. Okay, so I can remove this now. I have all the information I need, and let's get into it. We're going to let x be written in this form. Pi squared on 4 minus brackets pi squared on 4 minus x. Sorry, x squared. I mean, it's the same thing. For x, it would still hold, but we're looking for x squared. So what have I done? I've just added and subtracted a pi squared on 4. That's nothing. Now, where am I going to use that? Where can I see that I would use that? Well, I'm not going to use it in here because I kind of want this expression when I'm trying to get to my integrals. They're already popping up here. The place that I'm going to use it is in this x squared that's out the front here, because we always want to try to have pi squared on 4 minus x squared. And so substituting it into here, substituting that into here for x squared is kind of going to give us what we want. So let's get going. In equals 2q to the power 2n divided by n minus 1 factorial. So this first integral is actually just remaining as is. X squared n minus 1 cos x dx minus, now this is also going to get messy, 4q to the 2n, n minus 2 factorial. Okay, substituting x squared in, or this expression for x squared, will give me, firstly write our limits, and then we have pi squared on 4 minus pi squared on 4 minus x squared. So put that in square brackets. Okay, multiply that by pi squared on 4 minus x squared to the n minus 2. And again, I'm running out of room. And then I need to multiply that also by cos x dx. Okay. Now, in order to save a bit of room, I'm going to write this. And I mean, I'm going to have to write it eventually in terms of in minus 1. But I can write this in terms of in minus 1. So, in minus 1 is almost this. We have, let's just get this back here. I'll need q to the power of 2n minus 2, because I've distributed the 2 through, over n minus 1 factorial. So how can I get that? I have the n minus 1 factorial. How can I get q to the power 2n minus 2? Well, I can take out a q squared. So I'll have 2 q squared, and then I'm going to have q to the power of 2n minus 2 over n minus 1 factorial, multiplied by the integral, and that is exactly in minus 1. So that's convenient. We can write it like that for the moment. Now, let's manipulate this expression here. So 4q to the 2n divided by n minus 2 factorial. Now, I have, this is like having, here is term a, and here is term b. So I have like a minus b multiplied by this expression, which is like a c. This expression times that is like the c. So I'm really just multiplying expanding a bracket here. So let's go. That's going to be the integral of pi on 2, sorry, the integral from minus pi on 2 to pi on 2 of pi squared on 4 multiplied by pi squared on 4 minus x squared to the power n minus 2 times cos x, of course, I can't forget that. Now I'm going to break it up into two integrals straight away. So then for the next integral, it will be minus minus, so this is going to be plus 4q to the 2n over n minus 2 factorial. Now what am I left with? I'm left with, what's this? This is pi squared on 4 minus x squared, and I'm multiplying that by pi squared on 4 minus x squared to the n minus 2. So it's going to give me pi squared on 4 minus x squared to the n minus 1. I'm adding 1 to this power because this is the same as what's inside here. So my integral is going to be pi squared on 4 minus x squared to the power n minus 1 multiplied by cos x dx. Okay? Right, so now we need to try and write these expressions in terms of an in minus 1 or an in minus 2. Okay, so the first one I still have this, that's going to stay as is. Now, this is an n minus 2, so I want to try and write it as in minus 2 in some way. Now firstly, I'm going to notice that pi squared on 4 is just a constant. I can pull that out the front. And when I do that, I can cancel this 4 with this 4, and I'll have minus pi squared. Now, before I do anything, let's have a look at what n minus 2 would give me. If I substituted n minus 2 in for n, that would be q to the power of 2n minus 4 over n minus 2 factorial. So, here to get the 2n minus 4, that's q to the 4 times q to the 2n minus 4. And I have the n minus 2 factorial, and so now I've taken this out, I've taken out q to the 4, and I'm left with exactly I of n minus 2. That's good. Now what about the other integral? Well, remember this is an n minus 1, so I want it to be an in minus 1. And an in minus 1 would mean that this is q to the power of 2n minus 2. So I have to take out q squared, but I also need an n minus 1 in the denominator, an n minus 1 factorial in the denominator, but I only have n minus 2. So how can I get an n minus 1? Well, I could multiply top and bottom by n minus 1. And then here, this is n minus 1 factorial, and that's what I want. That's good. So I've created that n minus 1 factorial by multiplying by n minus 1 and n minus 1, which is multiplying by 1, which is fine. So I have that times n minus 1. Now I have exactly I of n minus 1, and there we have it. Now I just need to collect the like terms. So that would be 2q squared plus 4q squared n minus 1, I to the n minus 1, minus pi squared q to the 4, I n minus 2. Okay, what else can I do? I can I forgot to put a bracket around this. I can factor out a q squared here, and that'll give me 2 plus 4 n, distributing this 4 through, minus 4, multiplied by q squared, I n minus 1, minus, now, pi squared times q to the 4. Well, in the question, okay, before we go back to the question, let's have a look at what we're required to prove. We can see that I've pretty much got the first part here, right? I have this is 4n minus 2, and so times q squared, I n minus 1. I've pretty much got this. But here I have p squared q squared. There's no sign of a pi anywhere. But if I remember in the question, I was told that pi could be written as p on q. So therefore pi squared would be p squared on q squared. So pi squared is p squared on q squared times q to the 4, I n minus 2. Okay, simplifying here would be 4n minus 2 q squared I n minus 1. And simplifying here would be p squared, this would be q squared I n minus 2, which is finally, for 1 mark, I've used a whole page, proven what I want to prove. So we're happy.